All right, last thing we're going to look at is temperature change. Temperature change. Basically, here the idea is we're going to heat up the reaction system. And again, think about this as a mixture, right? You've got both gases in here. So let's get the example down there at the bottom. Hydrogen, iodide. These are all in the container together. So it's not that we have these separate from each other. They're all together, constantly going back and forth. So this is making this, and this is breaking down into this. You get that equilibrium. So I can't heat up this and not heat up the hydrogen and iodide. So keep that in mind. So if it's endothermic, we say that the reaction is going to absorb heat. We say that our reactants are absorbing heat. Remember we talked about endothermic absorbing heat. Exothermic, heat is being released. Remember, this has a negative value. This has a positive value when you're looking at the data. And you're probably going to see this symbol here, this delta H. We're going to talk more about this later. But delta H stands for enthalpy, but really what you could think of is that this would be heat. Okay, so this is the amount of thermal energy coming off or going into a reaction. So negative change in H or change in enthalpy would be exothermic, positive would be endothermic. So keep this in mind too. When temperatures increase, the equilibrium shifts in the direction that absorbs heat. So when we add heat, it's going to be absorbed. So which process absorbs the heat? Will it be the reactants or will it be the products? We're going to treat this just like we did the first one. So if you go back and you look at concentrations, this works the same way. If I add heat, it makes the reactants work more to create more products. If I take heat away, then I have to supply more heat because now if there's not enough heat, these aren't going to react as much and my products are going to then shift in that direction. Okay, so temperature changes, endothermic. Temperature changes, increase, shifts right, increases temperature for exothermic, it shifts left. Now again, I don't like to memorize that, but you can try to figure it out as you go through the problem. Okay, so here's what I'm talking about. Let's take a look at this example here. We've got the hydrogen and iodine forming hydrogen iodide gas. Here we're adding heat on this side, so this is considered an exothermic reaction. This is exothermic because it's releasing heat. Okay, so heat is a product. If you increase the temperature of the reaction, what happens to the equilibrium? Well, if I put more heat into the system, right, if the heat goes up, because the temperature is going up, we're going to have more heat available to break this down and shift the reaction in this direction. It's as simple as that. You add heat, it's used to break it down, shifts it further to the left. If I take heat away, if heat is going down, I'm removing the heat, I'm cooling it off, then the reaction will shift right. Now this is all dependent on whether the reaction is exo or endothermic, and that's what this is talking about. It's showing you the fact that one is the opposite of the other. So first you want to determine if it's exo or endothermic. You can write heat in as a reactant or as a reactant or as a product. It's up to you. You can just picture it there. It's fine too. And just treat it like you would a regular concentration problem. All right, if you have questions, I'll answer those in class. Let's look at the last little bit, which is how temperature affects K. Remember, we've talked about K being a constant. It will not change unless you change temperature. Okay, so K will change when you change temperature. And now the value of how K changes, it's just like the last slide there, depends on whether the reaction is exo or endothermic. Okay, now you could sit down and try to memorize this, but again, if you know me, you know that I can't memorize and I'm not going to be able to do that. But I can figure it out because I know is that K is products over reactants. I just keep that in mind. I can figure this whole thing out. All right, so let's say we go back to that last problem. Okay, let's say we come back to this and we say that temperature, there's an increase in temperature, and therefore the reaction, what's going to happen? We said if we increase temperature because we're adding heat, the reaction is going to shift left. Okay, now this is the only time K is going to change because of the fact that I'm adding heat. I'm changing the rates of the reactions. I'm actually literally changing their rates by adding heat. And this is a little bit more deep than we can get into right now, but just kind of bear with me here. So I want to know, will K, the new K that's formed that I get from this change in temperature, will it go up or will it go down? Well, what's happening to the reaction? The reaction is shifting left, right? Shifts in the left direction, shifts towards the reactants. Oh, okay, if it's shifting towards the reactants, well, we know that K is the products over reactants. So as I make this change, as the shifting is occurring, what am I getting more of? I'm getting more reactants and I'm getting less products, aren't I? So wouldn't it be safe to say that K is going to go down, right? So I can figure that out just by logically piecing together what I know about equilibrium and equilibrium constants. So let's go back and take a look at that last slide. We had an exothermic reaction, and the temperature change was going up, right? It was going up. So it increased. We shifted it to the left. I had more reactants, therefore K decreases. Again, if you want to memorize that, that's totally up to you. I would strongly recommend against that, but you know, it's up to you. All right, one last thing I'm going to leave you with here is the effect of a catalyst. Now, you should know that a catalyst speeds up a reaction, but a catalyst has no effect on our equilibrium position or the constant. All a catalyst does is gets you to equilibrium faster. That's it. It has no effect on how much. You're never going to get more products out of a reaction because you added a catalyst. If you think about that demonstration I did with the foam, I didn't get any more reactants than I would have if I let that go for hours on end. Now I just got there a lot faster. I speeded it up by adding a catalyst, and I got all of the oxygen to come out of that hydrogen peroxide really, really quickly. Okay? All right, so that pretty much ends a lesson on Le Chatelier's principle. All right, so hopefully you've learned something, and if you have any questions, I'll address them in class. See you later.